All right, good morning everyone. Welcome to today's lecture. Before we start, like usual, a few organizational comments. If you're still looking for a teammate, make sure to find someone. I recommend going to the TA sessions right afterwards and look around. Remember, you can also form teams of 3, so if you're alone, you can also join 2 people who have already formed a team. If you're looking for a teammate, you can ask the teaching assistants or me. We will try to help you find someone, but make sure to get active yourself. It's your responsibility to find a teammate. We are willing to help you, but you have to get active. We will not run after you and make sure that everyone has a teammate, so you have to get active. And make sure to make this soon, because the second assignment will come online most likely tonight, although the deadline for the first one is still ahead of us, but like I said, the first one is just a tutorial and the second one is much more work, so I hardly recommend to start with the second one early enough, which means you should find a teammate by now. In relation to the second one, there will be an introduction talk next Thursday in the lectures. Just be aware that this talk, that's probably not for you, but for the people who are hearing this now but not seeing me because they are looking at the recording. This talk will not be recorded because the teaching assistants are giving that, so I highly recommend that you're here. Tutorials, that is just a standard procedure, just a reminder that it starts today. Second tutorial will be online then on Thursday. And final comment, 2 people told me that that the old website is still online. That's not true. If you go online and see the old website, just refresh your web browser. I copied it, of course. I replaced the old stuff with the new stuff before the course started. But if you already looked at the old stuff before, then it could happen that it's still in the cache. So just refresh the cache of your web browser, and then it should be fine. Good. So let's continue where we stopped off last week, which are the basic mathematics that we need for computer graphics. So just a quick recap to refresh our memories. We defined vectors as n-tuple of scalar values, or by their length and their direction, to describe objects and to do arithmetics with it. So I gave you an algebraic and a geometric interpretation of a vector. Also introduced a couple of specific vectors like parallel vectors, unit vectors, and null vectors, which have certain characteristics that are important when we want to deal with them, or when we want to do arithmetics, which is then the second thing we talked about. So these are the basic definitions. And then we talked about how we can do arithmetics with those vectors. We introduced the scalar multiplication of a vector, that is a vector multiplied with a scalar. We introduced addition and subtraction, and we also introduced multiplications of vectors with a vector, but since this is not straightforward, there are different forms. One of them is the dot product or inner product or scalar product. I often use the term scalar product because the result of it is a scalar, in contrast to the cross product, where the result of the multiplication of 2 vectors is a vector. And then finally we introduced the basis or orthonormal basis as a specific case of a basis, which defines a 2D, or in higher dimension a 3D or a 4D space in which we can do something. For example, we can describe simple geometric objects that we use then for modeling when we want to do the computer graphics. And we started by circles and lines, and I told you that there are different ways to represent them, and one of them is the implicit representation of a line, and already that we can represent in different ways. For example, we can represent it also in vector notation, which has certain advantages sometimes when we do calculation, and also sometimes the vector visualization is easier to intuitively understand, especially for the implicit representation, because here we have one very special vector, which is the normal vector, which is a vector that is perpendicular to the line or to another vector, which we will see today later why this is a very special and very important vector. And with the implicit representation we can see it very easily and very simply, or if we have a normal vector, then we can create an implicit equation of a line or of a circle very easily. And also for those of you who have problems with the mathematics, realize that I also indirectly repeated some of the stuff that we basically take for granted because we think we assume that you learned that in high school. So I talked about trigonometric functions and Pythagoras theorem. So if you have problems with this, make sure to refresh your memory. And also there are chapters in the book about that that you can use. Good. So let's continue now. So I said there are different ways to represent those objects, and one of them is the implicit representation, which we talked about last time. And I said that one of the characteristics of the implicit representation is that we do not use it to calculate values explicitly, but it's kind of the shape that we're describing is indirectly defined by an equation. And if we want to have the points on that shape that make up that shape, or that if we want to draw that, we have to solve that equation to get the actual values of the shape that it represents. Now for the parametric representation, which is the second kind of representation we learned today, is that the characteristic that we can is that this representation allows us to calculate those values directly using just in 2D just a single parameter, or in multiple dimensions a number of parameters. In particular, we always need one parameter less than the dimension that we have. So if we start with 2D, of course we only need one parameter, and we do this by this equation here. So this is is our point P on a curve, which can be a random line here at random directions, and this is specified by two coordinates because we are in 2D, so we have x and y value, and those x and y values are calculated by two functions g and f, and you see they only depend on one parameter t, and the intuitive interpretation of it, or intuitive understanding of this is that you can basically see it as an index. So if you have a value t as I don't know, for t is 5, then you can calculate the x and y values for this t is 5, and if you want to then have the next value on the curve, you just increase t or decrease t if you want to have the previous value. So it is basically like an index that gives you all the numbers, all the points on the curve, and by increasing that index you can think about it as walking along that curve. Or if you draw it, you could also think about it as the time parameter. At a specific time you draw a point, and then if you continue drawing the next time step, you draw the next point, which is also why often the parameter t is used for that, because t comes from time. But in general it's just one single parameter that represents our curve. So like I said, intuitively we can think about this as walking along a line or this curve, and mathematically we model it by just having two functions that then are used to calculate the x and the y value. So let's look at a simple example to make it a little clearer. And of course one of the most straightforward examples is a line. So we see here that we can represent a line that goes through the 2 points P0 and P1 by using these two functions here. So these are the two functions g of t and h of t. And that of course might look a little confusing at first, but if you look at it in vector notation, you see here, if you remember how we defined addition and subtraction of vectors and also the scalar product, you see that this here can be seen as a vector P0. These here can be seen as the subtraction of two vectors P1 and P0, and this here is then just a scalar multiplication of this resulting vector with this here, and then we get the same line equation in vector notation. Now that is intuitively I think a little easier to understand, because we said that P0 and P1 are 2 points on the line. So if you look what we have here, if we make P1 minus P0, we actually get this vector here. So if this is P1, then this here is P1 minus P0. So this is minus P0. So remember we defined subtraction by just adding, appending the end of this vector to the beginning of the second vector to the end of the first vector, which if it's negative goes in that direction. So this here is then the vector p1 minus p0. So we see that this is basically this vector here on the line. Of course, how I've drawn it now is not the vector on the line, but it's basically a vector in exactly the same direction as the line, because I said also last time, a vector is just a representative of a whole class of vectors that have the same length and the same direction. So we have here a vector that specifies the direction of the line, but of course it doesn't specify the position of the line in a space, and that is what this vector p0 here does, because this vector p0 is, if we go up this vector p0, then we come to one point on the line, because that's how we defined p0, and then we have this if we add then this vector p1 minus p0, we kind of walk along that line, of course only to that one particular point. Now if we want to describe all points on the line, we just have to increase the length of that vector, and we know that we can do that with scalar multiplication, and that is exactly then where our parameter t comes in. So we see here in this equation, these are all fixed values except for t, which is the parameter, and that is intuitively basic. You can say you take the vector p0 to go to the position of the line in a space, and then you have the direction, and then you extend that direction as far to the front or to the back as far as you want to walk along the line, or to what kind of point on the line you want to get. Good. And this is also why sometimes these two vectors are called support vector and direction vector, or position and displacement vector. Actually, the way I explain it now would make it more intuitive to call the first one position vector, because it specifies the position of the line in the space, and the second one then the direction vector, because it specifies the direction of the line. And with this parameter t, then we can get to all points on the line. Now, so you see, this is I think, quite intuitive second description of a line, but like I said, sometimes the implicit representation of a line is more useful or could be more intuitive depending on the context. And also we have a third one. We have also the slope-intercept form, which is given by the slope and the distance here. So we have three ways to represent lines now, so it's important that we also, and since all of them are useful in a different context, or more useful in a different context, it also makes sense to convert them, or to know how to convert them into each other. I will not go into this here in the lectures, because first of all, you will do it partly in the tutorials, and secondly, we'll do it more often during the whole course of the lecture. We'll often do this transformation, so you will see that later on. And also, it's very simple arithmetics, but I highly recommend that you really do the tutorials and practice this. So just quickly, I mean, here it is, you see, it's really simple. It's very straightforward to go from here to here. We just have to bring everything to one side to have it equal 0 here. And the other way around is a little more arithmetics, but still very simple, because we just basically have to solve for y. So bring y on one side and everything else on the other side. And then we get the slope-intercept representation. This step here is a little more complicated, but also not very much. If we go from the implicit representation to a parametric representation, if you think about what we need for the parametric representation, we defined that by taking 2 points on the line. So we basically just need to take the implicit representation, get 2 points out of it, and then we can create the parametric representation. And we already have a first point, and the second one can be any point on the line, so we can just choose a clever one. So for example, we just set x equals 0, then we calculate the related y value, and then we have our second point and can write down the parametric representation. The other direction seems a little more complicated, because here we have a vector on the line, this one here, and we have the point, of course, so that's no problem. But we have here a vector on the line, and what we want is a normal vector, so we want to have this one. But if you remember one important characteristic of the scalar product from last week, then you will also see that this is actually quite simple, or we can figure out quite simply how that vector must look like. Because do you remember which characteristic is important here? Anyone? Okay, then you should really go to the tutorials. The scalar product of two vectors with the right that are perpendicular to each other is 0. So if we write down, sorry, if we write down the scalar product of a vector p with a vector n that we are looking for, then we see we get this equation, and this is 0. So we are interested in the n's, the coordinates of the normal vector, and we see xn plus y is only 0. That can only be fulfilled if either n is y minus x or n is minus yx, or of course if both of them are 0, but then we don't have a normal vector because null vector doesn't have a direction. So we see these are the only possible solutions for this, and so that means these are the only perpendicular vectors to this one vector, which means, of course, if we think about it from geometry, of course, it's obvious that we get two results here, because a right angle means it can have 90 degrees, but it can also has 270 degrees, because then we have a right angle here. So we see here, if this is our vector, then these are just the opposed, the two normal vectors that we have for this. So we see we just swap the lines, the coordinates, and change one sign, and then we have our normal vector. So this is pretty simple. Good. Now we know how to represent lines in parametric forms, but of course also there is a parametric representation of a circle. And again, we use two functions here for this. We use g of and h of, and this of here is our parameter. Now for the line, we said intuitively we can think about this as being on the line and then just multiplying the direction vector with a value t to get to the position, to get to each position on the line. Now that doesn't work with a circle. If we are on a circle and want to walk along the circle, of course, if we choose the same direction, when we walk along the circle, the direction constantly changes. So we cannot use a vector to describe that, but we can use, of course, an angle to describe that, because if we have a reference value, which in this case is the direction of the parallel to the xy axis, and here we have a point P on the circle. Remember, I forgot, I didn't update the images yet, so these are all vectors. Sorry for that again. So if you think about it, if we are walking along the circle now to go to all the points on the circle or to a particular point on the circle, of course this angle phi here that we have here is increased, or if we think about the other way around, by constantly increasing this angle phi, we can walk to all the points on the circle, we can reach all the points on the circle. So we see intuitively that this angle is an appropriate way, an appropriate parameter, one parameter to describe the two coordinates that we have for to make up the circle. The question is, of course, again, how do we come up with these two representations for these values? But again, if you think about the circle and the angle, it's pretty straightforward. We use just the trigonometry, where we had a similar case with the length of the vector, where we calculated we used the Pythagoras. So this is just a recap of the trigonometry. Last week I talked about the trigonomic functions, cosine and sine, how the functions look like with respect to an angle, but you can also, of course, define them, or you also have trigonometric relations when you look at the triangles. For example, the cosine of a triangle with a right angle is defined as this side here, which is the side next to the angle and the right angle, divided by the opposite side of the right angle. This is the cosine, and now you see already this is the general definition of it, but I already used x, y, and r, and the reason for this is, of course, if I interpret this as a vector v x, y, then I see, of course, the length of this vector, a vector v which represents a point on the line, then the length of the vector must be the radius, and these must be the x and y values, coordinates of the vector. So if we write this down like that, you see for the x value and also for the y value, you get exactly what you have here on the right side. So that allows us to describe a circle around the origin, but of course if we want to describe a random vector, we also have to add the center. So what we basically do is we describe the circle here, and then we move the center to here from the origin to here, but that also means we have to move all points by the same length and the same direction to this, for example, this point here to this point here on the circle. So this is also the vector C. Now if you compare this with what we had with the implicit representation, probably you realize that for the implicit representation we had a minus C, whereas here we just add this vector. But I also explained it the other way around. I explained it intuitively as saying if a point is on the circle, if and only if this distance here, which is P minus C, has the same length as the radius of the circle. So which is basically kind of shows that this is the implicit representation of it, where the values are implicitly encoded, whereas here we have the parametric representation where we can explicitly calculate directly those parameters, which is why I've chosen intuitively to explain this intuitively by constructing the circle. And the other way I said, okay, this is the circle, so that must be fulfilled. And that is why also in one case you go back and you have the minus C. In this case you're adding C to construct it. So that is a nice illustration also of the difference of the major characteristic of those two. Good, so now we have all the basic stuff that we need, at least for now, to describe a few basic geometric objects, but of course just in 2D, but in graphics we want to deal with 3D, so let's just extend it to an implicit surface, the implicit curve to an explicit surface from 2D to 3D. And the generalization arithmetically, this is pretty straightforward. We just add another coordinate. Geometrically, of course, we run into problems because then I would need to draw 4 dimensions, which is quite impossible. So, but you get the idea, especially I think you will get the idea when we look at the example. So let's start with the implicit sphere. So if you look at the equation, if you remember the 2D case, then you see we're just adding a third dimension or a third coordinate here. So we have the center of the sphere and the radius C and R, and P is then a random point on the sphere, only now the point is in 3 dimensions, so we have a third coordinate here. And similarly to the 2D case, we can intuitively or we can arithmetically make sure that this is correct by saying again that P minus C, so that is if this is the point P on the line on the sphere, sorry, and this is the center, then this here is P minus C, and the length of this vector must be R if the point is on the sphere. So we can write it like this, and then if we make both sides to the power of 2 and bring everything to one side, then we get this equation, and then we see that the length is defined as the square root of this vector of the coordinates to the power, which is then again the same as the scalar product. And if you write this down, then you will see that you will end up exactly with this equation that we have here at the top. So this does indeed represent all points on the sphere. And in the same way as the sphere is a generalization of the circle by just adding the third coordinate, we see that we can say that a plane is a generalization of a line by just adding a third coordinate. So if you look here, this is similar to the line equation, only with another factor here, which is the third coordinate. Again, you also remember that we said we can write this in normal vector, in vector form, and in that case we have these coordinates here, which are the normal vector multiplied with the vector p, which is now x, y, and z, minus a point p0, which depends, of course, on this value d. And if you remember the 2D case, then I started with ax minus y, or was it minus ax plus y? I think it was minus x plus y minus d minus c equals 0, something like that, not sure. But you remember we had only here a 1, and only in the general form I used an a. The reason for I used a scalar here, a multiple scalar here. The reason is, of course, if it is equal to 0, then we can multiply it with any other value and the equation doesn't change. But if it is 0 here, then it makes the calculation easier, because in that case the c just indicates the distance of the line to the origin. Whereas here, if we write it in that case, then of course we have to check what does the p-value mean. If we set here x and y equals 0, so if x is y equals 0, then we get here c set equals d, and that means, of course, that we have the set value here is d divided by c. So if we look at this, this is d divided by c. So then you see, of course, if you have, before that, if you multiply it with 1 divided by c, this is 1, and then this thing here at the end, the minus d, which is then a different d, of course, represents exactly the distance of the plane to the origin. So you see here, this is a straightforward generalization of the 2D case to the 3D case, of the line in 2D to this plane in 3D, and even this this distance here is the same. And intuitively, the intuitive interpretation of this is similar also to the line. You have the distance that shows you, gives you a position of the plane. We can look at it like this. If you have here three-dimensional coordinate system, so our floor is the xy plane, then d divided by c gives you the position of the plane, and then you have a normal vector here, and then you give the direction of the plane, and by these two characteristics you are able to uniquely specify the position and the orientation of the plane in 3D. And this was an example where it's clearly an advantage to be here online and not listen to the recordings. Good. So we see we can represent 2D. We can easily go from 2D to 3D with this implicit representation. It's pretty straightforward. The question is, of course, if we go from 2D to 3D, we do not necessarily only have objects that are really two-dimensional object, but we can also have like one-dimensional objects in 3D, which is of course not formally correct, which is why I put it here in quotations. But you can imagine, for example, this curve here, or a line in 3D. A line is, we also want to represent lines in 3D, of course, and the line is, of course, in 3D, it's 3D, but it's kind of a one-dimensional thing, because we can control it also with a parametric representation with one parameter. Unfortunately, there is no implicit representation of one-dimensional things in 3D. We could, of course, say, yeah, we just use two coordinates for that, but then we get degenerated surfaces, so that doesn't work. What we can do with implicit representation is we can calculate intersections of them, and they are then one objects that have this one dimension lower. An alternative would be, for example, if we have two planes here, and then we calculate the intersection of these two planes, we get a line. So you see, you can use the implicit representation to create these one-dimensional things by calculating intersections. But of course, that is not really that easy and that straightforward. But fortunately, we can use the parametric representation to do that. We just need to add a third function here, and then you see, if you think about this intuitive index representation, or if you think about a parametric curve as an index that allows you to access or to calculate all points on the curve, then you just need to add it here, and then here you just have here your t, and then here you have your t plus 1, and so on. So this should work pretty straightforward, and we'll see, I think in the next tutorial there will be an example for a line in 3D with this kind of case. Here I have another example, which is actually a spiral. So I was trying to draw this last year, but this doesn't really work out that well, which is why a student was nice enough to make a movie and send it to me. So here do you see the function here is that for x we say we have the cosine, so this is x. For y we have the sine, and for t we just for z we just go up the t-axis. So what we do basically is we add up these two values and do the middle, choose the middle value between them. So for t equals 0, we have this value here and this value here, which means in the middle we have it. Oh no, if we add it up, we start here, and then we move to the right, and here we move up, and then end up in this spiral. Yeah, it's really hard to draw, but it looks like this, and you can hopefully see it better from this little movie clip here. So, or maybe I scroll through it, that's better. So you see you start here at the bottom. Red is x, it's a little the other way around that I draw on it. Green is y, and t is just the value, the z-axis that goes up. And the black one is then the combination of the two values. So you see here how they add up. And here, for example, if x, the red one, is 0, and the green one is the maximum, you come also to the maximum. And then the x increases again, which makes it drift a little bit to the left. And you go here, and you're right, and then you get a spiral. So now it would also be good if I could turn it around in 3D. So if anyone is motivated to do something like that, send it to me. I show it next year then. Good. Yeah, so this is what we get. All right, of course, so we see that works, but of course we are mostly interested in or we're also interested in these kind of objects that depend on two parameters that are really like 3D objects, like planes and spheres, like we talked about with the implicit representation. And this is again just straightforward generalization of the 2D case. Like I said, for a parametric representation, we always need one parameter less than the dimension that we have. So if we move from 2D to 3D, instead of one parameter, we now two parameters, and we have three functions. We have f, g, and h, and you see they depend on two parameters. And this again becomes hopefully clear when we look at the simple geometric shapes. So let's start with a sphere. So a sphere in 2D, for a circle, we said it's clear that one angle is enough to describe all points on the circle. But of course, if we do this in 3D and we just have one angle, then we can just go around the circumference of the circle, but we cannot of the sphere, but we cannot reach all of them. So the idea is basically to say we use one angle to go around the circumference, which could be, for example, the xy plane, and then we use another angle to go in the third dimension, so to have another circumference, which is orthogonal to the first one, which is then the z-axis. So we use an angle phi to go around the circle in the xy plane, and then an angle, if we have, for example, reached then a point that we want to reach, which is this one here, we just go up or down by an angle theta to reach then finally that point that we want to have on the sphere. And this is, I'm actually pretty sure that most of you already are familiar with this, because this is how we describe positions on Earth, on the globe, by using the longitude and the latitude, which is exactly the same. It's just two values. One is horizontal, the other is vertical, to describe a point on Earth, or in this case on an abstract sphere. And again, of course, this is the intuitive interpretation, and the difficult question is, or it's mildly difficult question here, is how we get the equations for that. And again, we get this from trigonometry. I've already drawn it here to illustrate this. If we have a vector p on the sphere x, y, and z, and then we can describe this by two angles. So for example, the phi angle, like I said, if we use this in the xy plane, that would then be this angle here. But then we see from the, since this is also a right angle here, we see that this here is the distance x. So this x here is this x here, of course, from the vector p. And then we see that this is the cosine of phi. is x divided by, let's just call this here p dash, because it's the projection of p on the plane. Remember, we talked about projections last time. So this is the length of this part here. And then we go up with the vector theta, which is this one here. But since this is a triangle with a right angle and this is a right angle, we know that this must also be the vector theta, the angle theta. And that means that the sine of theta is defined as p dash divided by r, which is this length here, which is the length of the vector, or if the vector is on the sphere, it must be the radius. So we get sine and cosine. Now if you put this into here, then you see the p comes out, the r goes out, and we just have x left. So this does indeed represent the x-coordinate, and you get the same for the y and the z coordinate. I'm not going to write this down because it's pretty straightforward, but I highly recommend that you do it at home. So again, you see that we use simple trigonometry to get from the related triangles only in 3D now to get these equations here. Of course, and then again, this allows us to describe a circle around a sphere around the origin. But if we want to have then a sphere around a random point, again we do it like last time. We just add this value here, the new center here. So if we move the center from here to here, then of course all points on the sphere also move about the same length and the same direction, and then we have here our new sphere around the center, if you draw it a little nicer than I do. Good. Yeah, and this looks of course now a little less so for the parametric representation of a line, it looked more, I think it looks more intuitive. The parametric representation of a line looks more intuitive than the implicit representation of it, whereas for the sphere probably you would say that the implicit representation seems more intuitive than the parametric one. But we will see later when we do, depending on what kind of calculations we do, for example when we do the texture mapping, that the parametric representation of a sphere has certain advantages in that situation. You will see that pretty soon in the practicals, I hope. Good. So we have parametric spheres. Now we can also describe parametric planes, of course. And if you think about a plane, we actually already described a plane, but in 2D, which is our 2D space, because a 2D space is nothing else than a plane in 2D. It's just the space is the whole object. And what we did there is we said we have it's enough to have two base vectors to describe or to address all points in our 2D space. So if we generalize this, if we see this 2D space as a subspace of our 3D, which is then just our plane that we want to describe, we can basically say if we're on the plane, we can use a linear combination of two vectors that are on the plane to describe all the planes, all the points on that plane. So if we have here a vector v and a vector w, we can make a linear combination to describe all the points that are on this plane. And you see here, that's what we have here in the parametric equation on the right side. We have this linear combination of these two. Now they are not base vectors. In the 2D case, they would be the base vectors. Here they are just vectors on the plane. But of course then that works only if we are already on the plane. So we need also the information about the position where the plane is in our space. So we need an initial reference point in our 2D space. That was the origin. Here we just take one point on the plane. So we have a point pointing, a vector pointing to a point on the plane. This is our P0. For example, could be any point on a plane, and then we have the base vector, these vectors on the plane, which are like the base vectors in the 2D case to describe it. Good, and so you see we just need one vector to a point on the plane, and we need two vectors on the plane to uniquely specify our plane. But of course we could also specify our plane similar like we did with the line, where we used 2 points on the line to specify uniquely the line. We could also use 3 points on a plane to uniquely specify a plane. And if you do that, of course, then you need to be careful that here you have only 3 points on the plane. But if you then want to use the linear combination, you need 2 vectors on the plane. So you need to make, for example, the subtraction of 2 of these to get your 2 base vectors on the plane. So that means you have to write it or calculate it this way. Just be careful, because that's a very common mistake in the exams. Good. All right, so now we can use 3 points to specify a plane, but we can also in our 3D space use 3 points, of course, to specify a triangle, which is very important because a triangle is probably the most important geometric object that we are dealing with in graphics. The reason is, of course, because first of all, we can model a lot of things very realistically with triangles if we make them small enough, and secondly, they are easy to calculate. And this is what we're trying to talk about now. So if we have 3 points, we can specify a triangle. But of course, we also need to know, if we want to draw a triangle on the screen, we also need to know which of the points of this plane that the triangle is on are within the triangle. So if we have a point, it's not enough to just know the corner points. We also need a mechanism to specify which point is on the triangle. And here it comes in very handy that we can express all geometric objects in different ways with different coordinate system, like I already said last time. And for triangles, these so-called barycentric coordinates are quite useful. So let's first look at the Cartesian coordinates. In a Cartesian coordinate system, we have 2 unit vectors that are orthogonal to each other. So in 2D, or if we have, for example, in 3D, we have here 0, 0, 1, for example. We have here 1, 0, 0, and here we have 0, 1, 0, and then we can define all triangle or all points in that space by a linear combination of them. So this is a 3D case for simplicity reason, and because it's easier to visualize, I've restricted myself here to 2D, but the generalization to 3D, as you see here, is quite straightforward. So what we basically do with this is we define some sort of a grid, and within that grid we can then access all points. Of course, if we implement that and the grid are pixels, we can only address the center of the cells or the corners of the cells, but if we do it in mathematics, in our abstract geometric model, then we can address, of course, all points within also. And so you see we have this grid, and then we can specify all the points of the triangle within that grid. But now we can say, and we know that this works because we said these 2 vectors define a base. So this here is, for example, for C, this is, let's call it CT times B2, and this here, and this here is then CS times B1, and then you see this defines the point C of the triangle. Now, but we also said that we can do this not only for vectors that are orthogonal to each other, but with any 2 vectors that are non-parallel, that are linearly independent, including, for example, the corners of the triangle. So we could use these 2 vectors here to also as a 2D as a basis to represent our 2D space. We just get a different grid, which in that case is a grid of parallelograms instead of squares like in the previous case. But again, by multiplying, if we take this as the base vector, multiplying that with a multiple, for example, gamma, and that one with another, oh wait, sorry, that was wrong. That one with a parameter beta, then we see we get, what was that? That's nonsense what I'm drawing here. problem is that in the previous case I could use C as an example. Here it doesn't make sense because in this case beta would be 0, so it's better to just use P as an example. Here we have P, so if we multiply this vector with gamma we go to here. If we multiply this vector with beta we go to here, and that means we can describe the point P here with a linear combination. We just need to use different base vectors here. And also I'm using, you see, Greek letters now to distinguish it from the Cartesian coordinate system. So this is just a notation that makes it also easier to see that there is a difference. The other way where we see there is a difference is, of course, this vector A here, which we didn't have in the previous case, but that is, of course, because we're now going from this position. So our base vectors are placed here at this position, which means if we have the origin here, we first have to get to this position. So we just add this vector A to it, and then we come to this point, which is then the new origin, basically, of our Bayesian coordinate system. And that has certain advantages when we want to calculate, when we want to represent triangles. And yeah, we'll discuss this after a break. So let's make a break till 10 o'clock.